going back to what we did last class. In our last class, we were building a tree that wasn't a binary tree, but a tree that was called a 2, 3, 4 tree, which allowed me to get more data in a node. I had more pointers in a node, and I could be able to search faster. So I'm going to start running through a couple of numbers from class the other day. 53. See, my handwriting is nicer with a pen, but I think you need the marker to see better. Is that true? What's better, 53 or 27? Are they about the same?
They're about the same.
They're about the same. 53, 27, 75, 25, 70, 41, 38, 16, 59. So if I started to build this, you want a couple minutes to try it on your own first? See if you know what you're talking about? Yeah, let us try it on our own first. Okay, that sounds good. So right now, you're going to build a 2, 3, 4 search tree. I left out the word binary. Buddy of mine just sent a picture to me how it's snowing in State College. Keep it up there. We don't need it here. Mm-hmm. 53. And I know my next number caused a problem. My next number caused me to have to split. So if I'm going to put 25 in, it's going to go on this side. So over here, up here is going to be the 53. Over here is a 25 and a 27. Over here is a 75. So far, so good. Now I have a 70 and a 41. So 53, 25, 27. It's a 53. So I'm now about to add the 70. 70, 75. And the next thing I add is a 41. 25, 27, 41, 70, 75, 53. And the next number I added was a 38. 38 made this node blow up. And what did it do? Sent the middle term up. So the 27 is going to go up with the 53, 25, 41. So at the top, I have 27 and 53. I have 25 to the left, 38 and 41 to the right. 25 to the left, 38 and 41. And out here was 70 and 75. Okay, so I had some movement here where my parent got filled and I had to split it and build down. And then I keep adding. And when my node down here, my child node blew up, it had to go back up if it could. And we kept going from there. We talked about coding this, and we were like, yeah, no, maybe not. All right, so we're going to hang on to that because today we're going to talk about something called a red-black tree. And a red-black tree is a BST. Hopefully we are starting to learn what a BST is. It's a binary search tree, okay? But this time, so binary search tree means it's no longer going to be a 2, 3, 4, but it's going to be back to a binary tree where I have a left and right, but it's going to keep the same principles as that 2, 3, 4 tree. And you'll see that in a minute, okay? So this is called a red-black tree. Same idea as 2, 3, 4, but we're going to represent it in a binary tree. All right, so every path from the root to a leaf has the same number of black links. So when we get ready to start drawing our nodes, we're going to be connecting them, as you can see down here, with a black, which really is blue, a black or a red link. Okay, so that's going to become important, and I'll show you in a minute. No path from the root to a leaf has 2 or more consecutive red links. So from the root to every leaf, it's going to have the same number of black links. No path from the root to a leaf has 2 or more consecutive red links. All right, well, let's talk about what a black link is and a red link. And I'm going to demonstrate it here. Say we have a node with X, Y, and we're going to connect to a node called A, B, and C in this way. And what happens here is, if you think of the 2, 3, 4 tree, siblings are connected by red, children are connected by black. So a way to represent this X, Y, A, B, and C tree is X and Y are in fact connected by, so if Y was my root, X would go to the left, but they're connected by red because they're siblings. Children coming down from X would be A or B. Children coming down from Y would be C. I can tell I wrote this when I was sleepy because it's really sloppy. Another representation of the same thing would be over here, where X is a node in a node, it's the data item. Its sibling is Y. To the left of X is A. To the left of Y is B. To the right of Y would be C. To the right of Y is C. To the left of Y. Okay? Again, from the root to every leaf, it has to have the same number of black nodes or black links, okay? 1, 1, and 1, and no more than 2 reds. Here's another example, X, Y, Z. These are all connected by blacks. Well, I'm sorry, this is just a 2, 3, 4. And I could represent it this way. Sibling are red. From root to each leaf has the same number of blacks. So now you have an idea of what it looks like. Now we actually have to try to build one and see if we can pull this off. All right, so I'm going to start with the same list we just worked on for 2, 3, 4. And I'm going to go down this, keeping this guy in mind, because in my head I know that siblings are red, and down to a child is going to be black. So let's see if we can pull this off. I'm actually going to switch to a pencil case I mess this up. And we're going to go red, black. And something in here is going to happen. You're going to go, oh, crap. But that's okay. So my first node is 53. And I just add 53. My second node is 27. Where do you want it to go? Left or right?
Left.
Left. Yeah, it's going to have to go left. So now I'm going to have a 53 and a 27 to the left. And it has to be connected with a red because they're siblings. If I now add 75, it's greater than 53, but it would still, it's still considered a sibling. I would connect it with red. So up to that point, everything's good. All right, so the next number I add is 25. So now I need to start really putting some thought into this. It's a binary tree. So I'm going to be going left and right of 53, and I need to see what's going to happen here. 25 is going to go to the left here, and it's going to go to the right here. So if I start writing this, I get 53, 27, 25, and 75. Well, what happened? All of a sudden, I had 25 come into play, and I'm okay with all of that. And by my cheat over there on the left, I know what my links should be. What should it be from 53 to 27?
Black.
Yeah, it should be a black. What should it be from 25 to 27? That should be a red. And from 53 to 75, that also looks like a red. So let's see what happens. I added a node, okay? And I'm trying to think coding wise. So right now I have a red, a red, a red, a red, a red. So if I added 25 and, you know, what am I going to do to change all of these links from one color to another? Well, when I add, let me ask you this. Up here, I started with 53 and I added 27 and it went down 1. What color was it when it went down 1?
Red.
Red. So it looks like when I add a red, you know, when I add a new data item, left or right, it's going to start out as red. When I added 75, it went to the right of 53. It's going to be red. So I'm starting to think now, okay, when I add, it's going to be red. What happens if I add, and now all of a sudden, I have 2 reds. So I added this and I have a red. Okay, so here's a red, here's a red, here's a red. And when I added, I got 2 reds in a row. And one of my rules was I couldn't have from root to a leaf 2 reds in a row. So what happened to these reds? Okay, well, I already know the answer, right? The answer is I went from here and I had to split this guy up. So when I added this red right here, these guys changed. So this stayed a red when I added it. When I added this, it became a red. And the result up here was now a black and a black. So when I added this red, I had 2 reds in this path. Boom, boom. It had to change some things. So it went up and made these guys black. Now, coding this, this is just like so many other things we've been looking at. It's one of these where we would have to look at the concept over and over and over to figure out how to code this. Because eventually this would be a nice search tree, similar idea to what's here, but we're representing it as a binary tree. All right, shall we continue with the fun? Starting to get a little bit of an idea of what's going on here. So now I'm going to add a new number. I add the 75. Excuse me, I add the 70. So I come in, it's greater than 53. It's less than 75. It would go here. And I would have now a red. So when I put this in, it's going to be a red. Does that cause any problems? Do I have the same number of blacks from root to all leaves? Do I have two reds in a row? I think I'm okay. So I now have this tree, 53, 27, 75, 25, and 70. And we just made this a red, and this was a red. So far, so good. Okay, so again, what's the purpose of this? The purpose of this is sorting or searching, excuse me. I want to look for a number. Say my number is 28. Okay, what is the advantage of having the reds and blacks? So if I came over here and I wanted to look for 28, I go to the left. I check these. There's no remember, there was an advantage to doing this. Okay. Is there an advantage of representing this red-black way? How would I look for 28, 53, 26? There's no bonus. What is the red telling me if I was looking for, what does black tell me and red tell me if I'm searching? Or is a binary search tree itself just good and done?
Well, it helps on insertion. Does it help on searching?
It helps on insertion. In what way?
To keep it balanced, since you're not just inserting them at the end all the time, and you get unbalanced trees.
Okay, but when I did a normal binary tree, if I remember right, I inserted them. I went and decided left or right until I hit a null, and then I put it in. So this is easier to insert than this, okay? But my question again goes back to, why not just make this a binary tree? Well, let's keep going, see if we can answer that question. All right, the next thing after I added 70 was 41, and 41 would go here. I inserted as a red. Does it meet all of my rules? The answer is yes. 53, 27, 25, 41, 75, 70. Sibling and sibling and sibling and sibling. Uh-oh. What's going to happen here in a minute? I got all this and I'm having fun, and all of a sudden I know this guy is now full. I have two reds here. I still meet all my rules. What happens when I add a new number over here? Uh-oh. That's exactly what I did here. I added 38. So now if I add 38, 38 looks like it's going to sit right here. Okay, I'm adding 38, and when I add it, it's a red, and I have all kind of chaos going on. Well, guess what's going to happen here, folks? Come on, it's fun. You can guess it. Anybody want to guess? So now I have two consecutive reds. Okay, I can't have that, but I have to have the same number of blacks coming down. And what basically happened here is 27, 41, and 38. What happened to the 27 when we did this? So when I added 38 to this guy right here, where did the 27 go? I know it's not the most exciting, but it's kind of cool in a way. When I added 38 to this node, 27 went back up and became a sibling to 53. Yeah, okay. So let's draw this. Let's draw the result, and then we'll go back and look and see what happened to the tree. In fact, here's the tree. 53, 27, and 75. Let me write the tree. 53, 27, 55. I'm sorry, 75. 25 and 41. A 70 and 38. Okay. And my reds were 27 to 45. And a red was 75 and 70. Okay. So here's what's happening. I'm now going to add 38. 38 is going to sit right here when I add it. And when I add it, this guy is a red. And my reds cause problem. So something has to happen here to match this. Well, I'm going to cheat and go backwards. I'm going to draw this, okay? I'm going to draw this and see how it compares down here. What do you think about that? Say go for it.
Go for it.
Go for it. Okay. So thanks. I am going to figure out, this could be one of two ways, right? 27 could be my root, or 53 could be my root. Let's take a look at both of them. If 27 is my root, 53 would be over here. And what do I know about 27 and 53? They would be red. I don't know why I keep asking questions, because I keep answering myself. 25 would be over here. All right. Between 27 and 53, 27 and 53, I'm going to have a black link. And it's going to come down, and it's going to be either 38. So I have a couple of options of how this might end up. And 41 with a red, or it could be rotated around. Could be 41 over there and 30. But I need to figure out a way to do something here so that it ends up 53. Let's see, 53. This is a black, down to either 70 or 75. And one of those is going to be a red. So this could be a possible solution. But my problem would be, how can I get from here to here? Again, from every parent to every leaf, there's the same number of blacks, and there can't be two or more reds in a row. So that meets the criteria. My other choice, what if I put 53 up here? That means its sibling is 27, and that would in fact be a red. Okay. From 27, I have a black, which is 25. From 27, from 27, I come down and have 38 and 41. Okay. When I leave 53, I'm going to come over here, and I'm going to have one of these two, 70 or 75, and then a connector to the other one. So coming out of 27, I'm going to come down, and I'm going to hit either 38 or 51, 38, excuse me, or 41, and then the other one's going to come out of there as a red. Just like over here, I'm going to hit 70 or 75, and one of those is then going to come out as a red. Everybody understand what I'm drawing? Yes? No?
Yeah.
So I'm drawing solutions to this. Okay. Here's one possibility. Here's one possibility. It's almost like I need to create some rules, like, what stays. If I have a situation like this, should it be the 53 stays? Which one stays, and so on. So I'm going to take a look, 53 could end up being my root. 27 could end up being my root. Where has my little dog gone? So I'm going to come back up here, and I know this is what I just built because this is where I was going. And I'm now adding the red, and I need to know what happens with two reds in a row that could solve my problem. I'm looking for my geniuses. Y'all geniuses, right? Think back to something that we previously have done. All right, let's go back here. When I had two reds in a row, how did I handle it? If I have two reds in a row, did I have to change the order of my insertion?
No.
No. So maybe if I come back over here and say, I don't have to change the order of my insertion, all of a sudden, does it look like maybe I can use this guy? Okay. So I'm going to come back up here and I'm going to go, this now becomes 53. This guy is still 27. This guy is 75. Over here, I had a 70. Did I say anything about this needing to be a balanced tree? And of course, here in a second, I'm going to have the 38. The 38 is going to go over here. So going back to something we've done before, laptop is, what did I miss? You didn't miss much. Okay, so this now became a red, and something up, boom, 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 we had chaos. But what should now end up is 27 and 53 should be a red. 27 and 25 should be a black. 27 to 38 should be a black. 53 to 75 should be a black. 40 that a red and a red. All right, so we need to now compare, see what's going on. I hate eraser boogies. So when I inserted this, I had two reds in a row. And what happens when I had two reds in a row? Well, nothing happened to this side. But over here, when I had two reds in a row, this red stayed, that became black, and that became red. So you're starting to see a pattern. I got two reds in a row, and it looked like as I went up my tree, this now became a black, that became a black, and that became a red. So if you were actually asked to program this or write this program, this goes back to everything we've been talking through this whole semester of every time I add something, whenever I want to add a new data type or be able to create something, I'm finding out more and more and more and more that I have to be writing this stuff down in order to survive through it. Questions? Now, I'm going to switch gears because this is in the book and you could follow along. And this is going through what we had just done. And we were talking about color changes that happened. And that was when I got those two reds in a row. And so I just inserted the 38. What happens if I insert the 16 it goes as a red, and I'm okay because I still have a black, and a black. So it's the same number of blacks for each one. I have these dashed ones are red and everything's good. And then all of a sudden we walk into something that's just going to totally blow your mind because I add a number and look what happens. So when I added 59, I did a right rotation. So I had two reds in a row. And instead of this becoming a black and this becoming a red, I'm looking and going, wait, the problem could actually be solved with a little AVL rotation. And now all of a sudden you want to cry and go back to that same story of who thinks of all of this stuff? What's the whole plan? We're not going that deep into this, in case you were wondering. Okay, so we were good up to that point. And again, we had to do some scratching and stretching to figure out what happens here. We added this red, and then we had to bump up to make them all reds and black. These were our examples. You know, we just started scribbling some things. All right, so I'm going to let you give it a whirl because I know you like this, and make up a list of numbers and see if you can create a red-black tree and how far we can go. So let's start with some numbers. Numbers between 1 and 100. Give me something in the middle to start. It's going to make it easier for us.
50.
50. That's definitely in the middle. What else?
25.
25. Keep rolling.
75.
Yeah.
37.
37.
68.
68. 40.
9.
9. 42. 70. 75. All right. Let's see if you can do a red-black tree. And if you want, you can do the 2, 3, 4 tree to the left to make sure you're doing it right. I'm going to put you in small groups. That way you can. We have part 1 and part 2.
Are there meant to be 275s?
No. Let's make this last one a 76. Good catch. All right. Breakout rooms. What do we have? We have a dozen people here. Let's make 3 rooms of 4. Create, open. We're only going to do this for about 10 or 15 minutes, okay? Then I'll bring you back and compare with what I possibly came up with. Okay.
did it. Hopefully.
All right. I guess I could have stopped the recording. This recording is going to be a mess.
Just gotta, cut it together with like Apple Movie Maker or something.
Yeah. Yeah. Or I can just dump it on there as it is,
Hey, that's fine. I'll take it.
So you went through the steps. That means this group's going to be able to help me out, explain what's going on. Right?
If we got it right.
Yeah, that part.
I hope you didn't go through it and just go to the last one and say, we're done. We'll see. Should I bring them back?
Yeah, why not?
They're coming back. I think I have the 2, 3, 4 tree down. Hopefully all of you do, right?
We had the red black down.
Oh, you do?
That 2, 3, 4 is so confusing to me.
All right.
I'm
Yeah,
the opposite. I
more
like the
into
2,
that.
4.
Really? Oh man.
I don't think we had much luck with the black rod.
Well, we'll find out what folks have in a minute. All right, last group. Room 1 doesn't want to come out. I think they're back. You guys back? Group 1?
Yep.
All right.
Yes, but I still have no idea what's going on.
All right. Well, let's see if we can start with the 2, 3, 4. Make sure we have it mastered. So the 2, 3, 4. I have a 50. Boom. I have 25. Boom. I have 75. We're still good. I now want to add a 37, which when I look at this, I look at the middle number and go 37 smaller. So 25 and 37, you're leaving. 75, you're leaving. So the only thing that stays when it's full is the middle number. Okay. So I just added 37. The next number I'm going to add is 68. It's greater than 50, so it's going to go here. The next number I add is 40. It's less than 50, so it's going to go over here. The next number I add is 9, and 9 is going to come to this mess, okay? So this mess is now full, which I have room at the parent, so I'm going to send it up to the parent. 37's leaving, 9 and 25 stay here, 40 is now that second link. So as you can see, the 9 and 25 stayed together. 37 went up to that root node. 40 stayed to the right of 37. 68 and 75 are to the right of 50. If I look on the next page, I have my current. I'm going to add the number 42, which is going to go into here. I add 70, which is greater than 50, so it's going down this line. There's room in here, so I put the 70 in. Finally, my last number is 76, which goes to the right here. This guy is full, so 70 is going up. 68 will be to the left of 70. 75 and 76 are to the right of 70. And again, if I'm searching for a number, I pick a number. Is it less than 37? If it is, it goes this way. Does it equal 37? It's found. Is it greater than this but less than this? I go down that path, go down that path, go down that path.
So for the code, there'll be a lot of if
Yeah,
statements.
yeah. You'll have some logical operators in there with the ifs. We're just
Okay.
understanding the concept. We're
Okay.
not actually going to get into the coding of this.
Okie dokie.
Yep. Big sigh of relief, right? Okay. Again, I want to ask this question. If I have a 2, 3, 4, that means I can store 3 pieces of data. How many pieces of data could be stored in a level 1, 2, 3 tree? How many pieces of data could be stored in a 2, 3, 4 tree that has 3 levels? Talked about this the other day. I want to see if you can get it back. First level is 3. Second
level's
level,
12.
it's 12, right? Because each node stores 3 and there's 4 of them. The next level, each node stores 3, but how many of them are there? 3 times
12.
Nope. So out of each node, there comes 4 paths. So out of each node, there would be 4 paths. So 4 here, 4 here, 4 here, and 4 here.
16.
16. Yeah, and you start to see a mathematical pattern, right? The next one would be 3 times 64. So I could be adding these numbers up, so for that 3, for just the first level, here's 12 plus 3 is 15 for the next level. Here's 48 plus that 15, which was 63. So within 3 levels, I could store 63 numbers. That was the advantage of the 2, 3, 4. Building it was harder. Searching it was easier. Let's go back to red, black. Sounds like some of you have answers. Here's the 50. I added a 25. So I added, it's red. It's okay. I add 75. It's red. It's okay. By okay, it means there's the same number of blacks to each leaf, in this case, none, and I don't have 2 reds in a row. Now I go to add 37, which is a red. So now I have 2 reds in a row, and my conclusion for this is this guy stays as a red, but these 2 became blacks. So when I added this red, these 2 became blacks because it has to match what's over here. Again, reds are siblings, blacks are parent to child. Okay, I'm now going to add a red 68, which would go right here. So I'm still pretty happy up to this point. And the next thing I add after the red 68 is a 40. Okay, where would the 40 go?
Right of 37.
To the right of 37. So actually, I don't want that line. To the right of 37 is going to be a red 40, and I have 2 reds in a row. But notice what happens. I know what the result should be. It's going to be this guy. But how do I get this guy? Guess what happens here? The 27 or 25 goes to 37, goes to 40. Give me 3 letters of the alphabet.
ABC.
A, that's a good one to start. Give me another letter of the alphabet.
J.
Nope. Farther down the line.
S.
Keep going. Well, let's draw the resulting tree, right? Right now, this comes to a node, and I have a number with 2 siblings. The middle number has a sibling to the left and a sibling to the right. My new result should be 50. Comes down to somebody. Over here, I still have 75 and 68. And this is going to stay a red. This comes down to the 75 and the 68. But what's going to go in this block right here?
37.
37.
37, yeah. And what goes to the left is 25.
25.
And what goes to the right is 40. And this guy and this guy are both reds because they're siblings. So what happened from here to here? I did that AVL rotation, didn't I? So for some reason, I got two reds in a row going this pattern, and this was my time to make my rotation. And it's going to match up with what's here. So again, you would be filling a room with trial and error to pick up patterns of how you would make this work. The next number I inserted was, let's see, I put the 40, I put in a 9. The 9's going to come down, and I'm going to have two reds in a row when I add that red 9. And look what happens. Everything. This guy becomes a red. This stays a red, and both of these become black. So when I added this red, these two became black, and that became a red because 37 and 50 connected. Got it? So again, do you understand what we're doing? First of all, 2, 3, 4, because that's kind of helping me pick out the patterns over here with all the red, black, and how I would change all those.
Can you just do it with the 9?
With the 9 in?
Yeah.
So let's see, with the 9 in, I now have 9s over here. So I still have 50, 37, and 75. I have 50, I have 37, and I have the 75. And over here's the 68. So nothing happened on that side over here. This stays black, and this is a red because these two are siblings. Okay.
And that
Under
changes.
the 37, I had the 25 and 40. I had the 25 and I had the 40. And then I added 9. And 9 is less than 50. Oh, I'm sorry, it's tilted. Less than 37, less than, so 9 gets added over here. When I added it, this is a red, okay? Currently, red, red, and black. Currently, this is a red, this is a red, and that's a black. And my rule is I can't have two reds in a row. So because I added it, where I added it, and so on, this guy is going to stay red. These two are going to switch to black, and this is going to become a red.
So, and this the same is true if we have two blacks in a row.
Well, be careful with the blacks. The blacks can be in a row, but from every parent to every leaf, I have to have two blacks then. So if I had two blacks down this path, I have to have two blacks down to that leaf, two blacks down to that leaf. So we can have blacks in a row.
Oh, okay. It's just the red.
Right. So when I added this red, this now became a black, this now became a black, and this now became a red.
So we're just flipping everything in that on that part of the leaf.
That's
whenever we have two reds in a row.
in this situation. In this, I don't know what would happen if there were children down here, how all that would work. There are just so many scenarios you'd have to look at to try and pick up all these patterns.
Okay.
And this is one of those things where, you think, well, all the math is created and done, but there are lots of things that are higher level that you're now walking into. I mean, you haven't learned all that you need to learn. There's like so much stuff out there. And if you're into computer science, if you're into math, if you're into whatever subject, you're going to keep learning more and more about what you can do. But this is just kind of the whole clever red-black idea. Our original red-black that we did, or excuse me, our original 2, 3, 4 tree that we did the other day, that's what it would look like as red-black. Every path, see here we have blacks in a row. That's okay. As long as from every root to a leaf, there's two blacks. There's two blacks. There's two blacks. Two. Yep, they all have two blacks. And there are no two reds in a row. because then we'd have a parent with a child that's a red or becoming a sibling, and then another sibling, and that's just not the way it works. All right, again, every path has the same number of black links, no 2 or more consecutive red. Siblings are, in fact, connected by reds. Okay, so I want you to fill in this chart for me. This is called a B tree, all right? And this is what we were looking at with 2, 3, 4 trees, except I'm curious how much data we can store. For example, if I had a binary tree, my first level, I could store one thing. My second level, I could store 1 plus the 2. My third level, if I keep coming, and here they're talking the height of 0, 1, 2, and 3. We talk a height 1, like we would call this height 2. They're calling this height 1. Different books are telling you different things. Okay, but then I would add 1, 2, 3, 4. There's my 7, and then I would add 8 more. There's my 15. Okay, we just looked at a 2, 3, 4 tree. I could store 3 items in the first level, the first node. In that second level, I was able to add how many more? I did 3 times 4. Dude, I don't even know where my notes are right now. So I had, in this first one, I was able to put 3. I had 4 links coming out. In each of these, I could put 3 items. So there's my next 12. So this was 3, this was 12, 3 and 12. So if I combine these, I get 3. Now I'm adding 3 to get 15. Now I'm going to add, we said 3 times 4 squared. So I would be able to add, 1, 2, 3, 4. There's 3s for each of that. 1, 2, 3, 4. There's 3s for each of that. 1, 2, 3, 4. 1, 2. So I would have 16 more. So if I added 48 to that, I had gotten that 63. And the next one was to add 3 times 4 squared, which was another 48. Excuse me, 4 cubed. My bad. That would be 64 times 3. Add it to 63. What do you get? $255. Anybody else get 255? Anybody? Here's what I did. 4 to the 0 power minus 1 is 3. 4 to the second power minus 1 is 15. 4 to the third power minus 1. 4 to the fourth power, which is 256 minus 1. So I did a little cheating once I picked up the pattern. Stuff you learned in pre-cal. All right. So if my node is 10, means I could have 10 links coming out. I can store 9 pieces of data. How many could I store on that next row?
99.
So yeah, I have 9, and I have 10 of these coming out, and each one of those 10 can store 9. So my next number is going to be, I'm going to add 9 times 10 to the first power, because there's 10 of them, right? And that gives me, as Conrad said, 99. Very good. So if I allowed, I could store 99 elements in. I don't know if that's the most efficient way, because I'd have to keep checking and then go down between the numbers. I'm going to be adding 9 times 10 to the second power to that 99. Good. 999. And I'm going to add 10 to the third power times 9, which is 9 times 1,000, 9,000, 9,999. So within that many rows, I could store a whole lot of data. So you could pick the size that you want. 2, 3, 4 seems to be popular. It's covered. It's in the book. But I could do a B tree, which says I can pick a node whatever size I want. I could say I want to store 8 values. I want to store 8 values, which means I would have 9 pointers coming out to nodes that could each store 8 values if I wanted to. Okay, any questions? Any questions? All right, on Thursday, what do we have planned? Anything exciting? Thursday, we are going to start something called graphs, okay? Graphs. Remember, we have class next Tuesday. Next Thursday, we're off for Thanksgiving, and then we have a week after that. So we're down to our last 4